I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
That's one small step for man, one giant leap for mankind.
It's important to remember that when John Kennedy made the commitment to go to the moon in 1961, the United States had a sum total of manned spaceflight experience of one person, Alan Shepard, for a 15-minute, 28-second suborbital flight. If you add in the Soviet experience, Yuri Gagarin had done essentially one 90-minute orbit. So when Kennedy threw down the gauntlet to go to the moon, the entire human spaceflight experience was essentially about 105 minutes. Kennedy's speech and his commitment was marvelous in its brevity and its simplicity. What he said was, go to the moon before the decade is out, bring somebody back safely to Earth, and probably is one of the reasons why we were so fired up and why it worked so well. One part I think that's really important to point out is that after Kennedy told us to go to the moon, a paragraph or so later in the speech, he said something that I think is also really important. He essentially said that he was asking the Congress and the country to accept a new course of action which would last for many years and carry very heavy costs. In his opinion, if we were to only go halfway or change our mind in the face of difficulty, he felt it would be better not to go at all. I think that is a watchword or an important concept that we need to keep in our minds whenever we do something big like Apollo. One of the best books on Apollo was Apollo: The Race to the Moon by Charles Murray and Catherine Cox. And they point out that Apollo was not a spacecraft, it was not an engineering project, it was not a means to improve science knowledge. In effect, John F. Kennedy pushed a heap of chips to the center of the table with the Soviet Union on the other side and said, call. In other words, he pushed us and the Russians to do more than just simply do simple suborbital or orbital flights. So, the big question is, how did we go from that one 15-minute flight to walking on the moon in less than 9 years? My personal bias is that the answer to that question has essentially 7 key points: national will, money, heavy lift launch vehicles, landers, spacesuits, the operations practices that allowed us to manage human spaceflight, and luck. The first 6 are obviously things we have under our control. However, luck is not, but you should never make a mistake by thinking we weren't lucky on Apollo. We were incredibly lucky on Apollo, and the few mistakes we made showed us the way to not make that mistake again. In fact, it's really important to recognize that when Apollo 18, 19, and 20 were canceled, at a high management level, at some level, there was a certain amount of sigh of relief because management felt like we'd been lucky and we didn't want to push our luck too much. Let's talk about these individually. National will, I think, is the first and most important part of this. The folks that took us to Apollo at a management level and the younger people were people that had history in World War II. They understood that a combination of real solid industrial production and commitment was really important. The generation that went to the moon on Apollo was not only used to succeeding, it understood a commitment to a large long-term goal. The country felt that Apollo had a similar kind of commitment as World War II, and it fired up the nation like nothing before. And certainly nothing in some ways has fired it up since. I think the second key issue of Apollo was money. Apollo had financial resources that we can only dream about in the space program today, or for that matter, most programs. In 1961, at the time of Kennedy's commitment, the NASA budget was just shy of $1 billion, and Apollo received about 10% of that. At the peak of Apollo spending in 1966, the NASA budget was $4.5 billion, and Apollo received just shy of $3 billion. The NASA budget at that time was something like 4% of the federal budget. We receive less than 1% of the budget today. Heavy lift launch vehicles, and particularly the Saturn V, were another key part. The Saturn V remains the largest single launch vehicle successfully flown, either by the United States, the Russians, or any other program. The Saturn V was an incredibly complex 3 million part machine that essentially worked, with one exception, flawlessly through every one of its launches. Without the Saturn V, I don't think it would have been possible to do Apollo by the end of the decade. The other thing that's important about the Saturn V is that to build the Saturn V, we also had to build the infrastructure at the Cape to manage the vehicle, which included the VAB, the crawler, Launch Complex 39, all of the pad hardware, and the launch pad itself. And we still use that. It will be the mainstay of our manned space program for the foreseeable future. I think the fourth key part is landers. The fact is that building the lunar module was totally important in success on Apollo. Without the LEM, we couldn't have done the mission because it would have involved landing great big rockets on the moon, climbing way down to the lunar surface and taking those big rockets off the lunar surface. In any event, deciding to go lunar orbit rendezvous was just the start of the fun, not the end, and the lunar module was probably, prior to the Space Shuttle Orbiter, probably the most complex spacecraft that had ever been built. The lunar module was the first true spacecraft in the sense that it could only operate in a vacuum. It had no thermal protection system, so it couldn't successfully re-enter the Earth's atmosphere. One of the interesting things about the LEM design was because we didn't really know how hard it was going to be to land on the moon, Grumman built into the LEM a considerable thrust margin, probably more than was really justified for a simple flags and footprints mission. Consequently, when we went to later missions and built a Block 2 LEM, the LEM's payload capacity was sufficient to put on rovers, big science packages, consumables for 3 days on the lunar surface, and we even flew a telescope to the moon at one point. The fifth key part, I believe, is EVA systems. A good example of how far we came is during Gemini 9 in June 1966, Gene Cernan did an EVA in a modified, essentially Air Force pressure garment that was so hard to work on that he was unable to successfully complete the EVA. He was beat up physically. His visor was so fogged that he had to use his nose to wipe a spot to see through to get back to the hatch of the spacecraft. The suit was so immobile that his EVA was essentially potentially life-threatening. In 1972, essentially 6.5 years later, Gene Cernan again went EVA, this time on the lunar surface. He did 3 successive EVAs over 3 days and had nary a qualm. He compiled over 21 hours of solid field geology experience on the lunar surface, and he set a record which has not been broken. In less than the 6 years that it took to go from essentially Gemini to the first Apollo mission, the EVA system technology had improved to the point where EVAs became routine, and we're still building and using that EVA capability on Space Station. The success was a combination of, like all of this, a lot of hard work, good engineering, and a lot of experimentation. By the time we finished with Apollo, we had built over a dozen different spacesuits before we down-selected to what became known as the A7L and the A7LB spacesuits. In addition to that, we built a portable life support system, which was probably one of the most complex small pieces of hardware ever built. It went through 25 EVAs, both in Earth orbit and on the lunar surface, without a single major malfunction. A lot of people whose names we're very familiar with, like Christopher Kraft and Gene Kranz, invented the operations practice that enabled us to go to the moon. They literally made this up as they went. Nobody had ever done this before. If you've seen the movie Apollo 13 or spent any time looking at Apollo, everybody knows that the flight control teams, both in the front room and the back rooms, were critical to getting success on Apollo. But in addition to that, they developed the training techniques, the flight dynamics techniques, and everything that not only allowed us to successfully do the Apollo 11, but allowed us to successfully build on each successive missions to do all of the exploration we did on the lunar surface. One of the things that I think is really important is how flexible we actually were during Apollo. We tend to think of the Apollo missions all ran by a very tightly scripted flight plan, and nothing ever changed from Apollo 11 to Apollo 17. But on Apollo 11 and Apollo 12, when we went down to the lunar surface, the lunar module started from a 100-kilometer orbit, performed essentially a burn that took it down to 10 kilometers, and then from that low point did the powered descent into the lunar surface. Consequently, you use the LEM engine to essentially do the whole lunar landing. After Apollo 12, they realized that the command and service module had more than enough delta V, and from Apollo 14 on, for every lunar landing, the command service module did what was called the descent orbit insertion burn. That basically left the LEM with its full complement of delta V from the time it started down to the lunar surface from 10 kilometers. That margin enabled us to put on things like rovers, extra consumables, and led to the incredible success of Apollos 15, 16, and 17. And it was all because we were willing to stop as the program was going on and say, hey, there may be a better way of doing this. So the question is, what did we actually do on the moon? The Apollo program landed at 6 different locations on the lunar surface, starting with Apollo 11 and building through Apollo 17. Apollo 11 was essentially the final engineering mission that followed in the wake of Apollos 7 through 10. If you look at the mission of each of 7 through 11, they all had specific engineering boxes they had to check, such that the Apollo 11 crew could get down to the lunar surface. The Apollo 11 mission, in a sense, was the fulfillment of Kennedy's commitment: land men on the moon and return them safely to the Earth. But in addition, it had the objectives to prove out the EVA system, return the first science from the lunar surface in the form of a small set of deployed science instruments, and bring back a modest collection of lunar samples. The Apollo 11 landing was a cliffhanger, even beyond the fact that it was the first lunar landing. And a number of problems came up and had to be solved in real time. The first one was what was called the 1201 alarms, the computer saturation alarms, that came up in the final portion of the descent. It sent caution and warning alarms that were not ultimately serious, but nevertheless caught everybody's attention. Luckily, in a number of simulations prior to the Apollo 11 landing, these alarms had also come up. And one flight controller in particular, Steve Bales, went back, figured out what the nature of the alarms were, and so he could tell Gene Kranz that we could safely proceed and ignore the alarms. The second problem was that there were a combination of navigational errors that led to the vehicle essentially targeting long and heading outside of the pre-planned landing ellipse. The reasons were numerous, ranging from simple things like uncommanded thruster firings and essentially starting down slightly late, things like that. The bottom line, though, is when the crew pitched over, it was clear they were not going to be able to land exactly at the spot that they wanted to land. The third problem was that as the crew approached the designated landing spot, it was clear that the LEM was headed for a boulder field that was not appropriate to land at. And although Neil Armstrong essentially took a good look at the site and thought maybe if we land short, we can get close to big boulders that might be interesting scientifically, prudence took over and he proceeded downstream and landed at a more satisfactory landing area. The last problem, which was something that turned out to be an interesting problem throughout the Apollo program, was as the LEM went into its final descent from about 30 meters, the descent engine thrust sent out clouds of dust, which made landing, essentially the view of the landing site, obscured, not seriously, but enough that the crew really couldn't exactly see the ground that they were landing on. I think the really key lessons we learned from Apollo 11, which is something we keep learning, is that we need pilots flying the spacecraft. The fact is that if Apollo 11 had essentially been flying on an autopilot that the crew could not override, they would have either crashed or they would have had to abort. The second key lesson was that the lunar surface was covered up with a loose ground-up rock layer that was compacted below about 10 centimeters, but loose and fluffy on the surface. And that proved to be both a bane and a blessing throughout the entire Apollo program. The third is that smart, well-motivated, and well-trained crew members greatly improved the science return. A good example of it is that Neil Armstrong realized at the end of their EVA that there would be a lot of empty space in the rock box. And rather than come back with empty space, he basically took the shovel and filled that empty space up with scooped up soil, which became one of the key soil samples, not only of Apollo 11, but of the whole lunar program. And largely on Neil's initiative, the crew walked about 100 meters west of the landing point to get a picture of Little West Crater, which proved to be the first photographic evidence we had of lunar bedrock and the depth of that regolith layer. We jump forward to Apollo 12. Apollo 12 was our first step toward doing real science on the moon, but it was still an engineering flight. Apollo 11 proved we could land on the moon, but because of the various navigational errors, it landed outside of its landing ellipse, and in fact, for a while, we weren't even sure exactly where Apollo 11 landed. Apollo 12 had the objective of landing at a pinpoint spot. The question was, if we say we want to land at spot X, how close can we put the LEM down to that spot? In order to do that, they decided they needed an interesting target, and they decided that they would land within walking distance of the Surveyor 3 spacecraft, which had landed on the moon in April of 1967. In addition to that task, the crew would deploy the first ALSEP, or Apollo Lunar Scientific Experiments package, an array of science monitoring equipment that had a lifetime of about 3 years. Okay, so Apollo 12, I think it surprised everybody, perhaps even the crew, by making precision landing possible. In this case, they put the LEM down only 13 meters from their planned landing spot. That's less than 40 feet. That enabled the crew in the course of 2 EVAs to walk around and the lunar surface and get to the Surveyor spacecraft and bring parts back, proving essentially our first long-duration exposure facility. The ALSEP package proved their worth, although the deployment was time-consuming and it really took up one whole EVA. And then it proved that walking traverses in excess of 2 kilometers can be accomplished safely and easily by the crew members. Apollo 13, of course, everybody knows about, and it was a successful failure. The Apollo 13 mission landing point was considered to be sufficiently important that Apollo 14 was subsequently targeted to go to the same landing spot. The Apollo 14 landing mission was the first physically challenging landing site that we had. In other words, it was not flat Maria. I guess the best way I can explain this is the difference between trying to land in, let's say, Iowa and landing in the Appalachian foothills. And the EVAs that were planned were also considerably challenging. In addition to putting out another ALSEP package, the crew had a pull cart called the Modularized Equipment Transporter that was dubbed Shepard's Rickshaw that they would take on what was to become the most physically challenging EVA that was ever completed on Apollo. The plan was to climb up the rim of Cone Crater. Cone Crater was an approximately 300-meter wide crater that had punched through an important rock layer on the lunar surface that hopefully would allow us to date one of the most important early impact events in lunar history. The second key science point was that the site was overlain by material that appeared to have been ejected by Copernicus crater, which is one of the youngest large craters on the lunar surface. Assuming we could bring back samples of those 2 events, we could really sort of narrow in on the chronology of impact events that occurred on the lunar surface. Apollo 14 proved to have a number of serious challenges that unfortunately compromised science return. The most difficult of this was navigation and dealing with the terrain. The landing area, as I said, was hilly, and it was sufficiently steep that climbing those hills in the A7L pressure garment was very difficult, and pulling the Modularized Equipment Transporter essentially proved to be impossible. The second thing is the nature of the topography and the fact that they were, in some cases, outside of the site of the LEM made navigation very difficult. The reality is that when you're on the lunar surface, there's nothing that gives you a sense of how far the horizon is, how big things are in the distance. We don't have any telephone poles, we don't have cars, we don't have trees, the things that we use on the Earth to give us a sense of how far away it is to someplace. And the lack of those things made navigation on the lunar surface very difficult. After Apollo 14, the program sort of stepped back and started considering what to do with the remaining Apollo missions. And it was decided that the Apollo 15, 16, and 17 missions were no longer to be, in effect, engineering flights, but they were going to go to high-value science targets, spend a long time on the surface, and essentially do real solid exploration of the lunar surface that had not been effective or not been possible on the first three missions. The Apollo 15 to 17 mission went to the moon with enough consumables for a 3-day stay, and more critically, a vehicle, a car called the Lunar Roving Vehicle, that enabled the crew members to essentially climb on and drive off to the sites they wanted to visit scientifically rather than walk. Now, a lot of people have this vision that the Lunar Roving Vehicle went zooming along the lunar surface. And the fact is the Lunar Roving Vehicle did not go terribly fast. In many cases, it didn't go really faster than walking. The key part of using the Lunar Roving Vehicle was because the crew members were sitting down, their metabolic rates and their use of the oxygen in the portable life support system was sufficiently slow that essentially they extended the gas tank of the Bliss. Consequently, instead of doing EVAs that were on the order of 4 hours, using the LRV, now you can get 7 or 8 hours on the lunar surface and cover far more territory than you could go if you had to walk. Apollo 15 landed on a Mare surface, essentially a flat surface, but it was located between a very considerable range of mountains called the Apennine Mountains and along the edge of a rift in the lunar surface called Hadley Rill. The mission objectives were to explore both the rill and the highland terrain, to sample lunar highland rocks in place to determine what the composition of the lunar highlands were and hopefully bring back some of the earliest pieces of the lunar crust possible. And then to sample and photograph the rill to understand how lunar rills are formed and what essentially they're telling us about the lunar surface. In addition to those objectives, the Apollo 15 mission included an enhanced ALSAP array, which had a heat flow experiment, which would require drilling holes 3 meters into the lunar regolith. Not only would it give us an understanding of the heat flow from the lunar interior, but it would also give us the deepest regolith core that we would ever get on Apollo. So Apollo 15 was a tremendously successful mission. I think the first and foremost thing that the Apollo 15 crew was to bring back a sample which became known as Apollo Sample 15415, or the Genesis rock. This was a sample of the primordial lunar crust that was almost 4.2 billion years old. If you want to think of that in terms of, the entire history of the universe, that rock literally represents 1/3 of the entire age of the universe, and it is in fact one of the oldest rocks we've ever had our hands on. In addition to that, photo documentation of the wall of Hadley Rill enabled us to understand how lunar lava flows were erupted and changed and improved our understanding of lunar geologic processes throughout the whole history of the moon. In addition to that, the Lunar Roving Vehicle proved its worth. It took crews up slopes in excess of 20 degrees and at distances far beyond where the crews had walked on Apollo 11, 12, and 14, went out to, in fact, 5 kilometers. The Apollo drill proved to be somewhat problematic, particularly in extracting the core out of the lunar surface. It became so difficult that, in effect, it ended up having Dave Scott bang up his shoulder and screw up his fingers, and between the physical exertion, Jim Irwin was later found to have had some cardiac irregularities, which proved to be a minor heart attack on the lunar surface. The timeline and ground supervision at times proved to be problematic in light of what the crew was seeing in the field, which led to the understanding that when the crew's on the ground in the field, they are in effect the experts. Apollo 16 was the first and only, in effect, pure highland site that we visited on Apollo. When you look up at the moon on a given evening, you'll see the dark areas and the light areas. The light areas are what we call the highlands, and Apollo 16 was the only flight that essentially landed on a pure highland site. The mission objective was to collect geologic observations on a number of highland landforms, which were thought to represent volcanoes in the lunar highlands, as well as set up another ALSEP array. The mission was notable for a number of reasons. The first is that poor photography from previous missions meant that we really didn't have a good understanding of what the landing site topography was going to look like. In fact, the smallest thing we saw at the Apollo 16 site prior to the mission itself was about 20 meters in diameter. So the bottom line was that it was a pure flying job from pitch over to landing. And the reality is when the crew pitched over, they were seeing the landing site for the first time. In addition, the site geology turned out to be different from what the scientists had thought it would be before the mission. And consequently, a lot of the mission plans went out the window. However, the quality of the geologic training that the crew had enabled them to just basically take over and do a field investigation, just like they hadn't ever had any training on what they thought they were going to find on the lunar surface. The Apollo 16 results made it another extremely successful mission. It did point out that the best scientific reasoning can lead to the wrong conclusion, particularly when you're going someplace that nobody's ever been before. And what you have to do is learn to fall back on your training and move forward, regardless of what you thought you'd see in the first place. The samples indicated that the lunar highlands were geologically extremely messy. They were dominated by large impacts, and there was no evidence of lunar volcanism, contrary to what we thought we'd see before we went on the mission. The mission also showed that having crew members that had an extensive geologic training gave us the confidence to move forward without having to essentially have the ground drive the crew as if they were carbon-based robots. And the Apollo 16 crew did a fantastic job in spite of the fact that they were seeing something they didn't expect to see. Although the highlands turned out to be not as nasty a place to land and drive as we thought it might be, the fact is that young impact craters that we saw proved to be very difficult to work around. They're very rocky. You couldn't get terribly close to a very young impact crater with the lunar roving vehicle, and the interiors were very steep, and any thoughts we had of going down into the craters were not realized. There were some problems in the mission. There were some malfunctions with the ALSEP, partly because of the fact that the crew's equipment got hooked in some of the cables. In addition to that, the mission had to land about 2 orbits late. That led to a truncation of the third EVA and caused the science backroom to engage in a drastic replanning effort before the crew went out on their third EVA. Apollo 17 in many ways was the culmination of the Apollo exploration of the moon. It landed on perhaps the most challenging landing site, a Mare valley called the Taurus Littrow Valley in Mare Serenitatis. The valley was between 2 very high massifs, well over 3,000 meters tall. And initially, it was difficult, in fact, to fit the landing ellipse into the landing site. The mission was also noteworthy that the lunar module pilot, Harrison Schmitt, was the first geologist to fly in space, and it made for a different crew dynamic. During the landing, Harrison Schmitt was clearly Gene Cernan's co-pilot, but once on the surface, Schmitt took over as the lead scientist, and Cernan was his essentially backup field assistant. The mission was also noteworthy in that the crew traveled farthest from the lunar module, almost 10 kilometers, and drove up the steepest slopes, 26 degrees, of any Apollo mission. The Apollo 17 had probably the best science return of any Apollo mission. This was affected largely by the fact that you had a geologist on the crew, but you also had a commander on the crew who had his own set of observational skills and high-quality geologic training. And the dynamic between the two of them led to very impressive geologic observations. The landing site also cooperated in that it provided the best access to rocks that could be tied through things like boulder tracks to bedrock units exposed on the upper reaches of the adjacent massifs. In addition to that, we had the unprecedented find of iron soil at Station 4, which turned out to be an example of a lunar volcanic eruption. In addition, there were a number of new geologic tools which allowed more samples to be collected with very minimal hits to the timeline by simply scooping dirt off the lunar roving vehicle while you're driving around. There were a few operational glitches, as on Apollo 15, the lunar roving vehicle fender failed, and that ended up showering both the crew members and the lunar roving vehicle with dirt from the lunar surface. However, the ground got together and basically built through photographs, clamps, and good old-fashioned duct tape a new fender which proved its value. So I want to talk a little bit about why Apollo matters. You know, we look back on Apollo with a certain amount of nostalgia, but we don't always think about why Apollo was so important. The first critical thing about Apollo was it taught us that the moon is not simply a big dust ball collected up from the remnants of the solar system formation. Prior to Apollo, we thought that the moon was essentially a big dust ball, and that processes both on the moon and by implication the Earth were essentially, through most of geologic history, quiescent. The reality is we discovered that from the Apollo samples that the formation of the moon was incredibly violent, involving massive impacts and essentially melting of the moon itself down to several hundred kilometers, something that prior to Apollo wasn't even considered possible. And in addition, the implication was if it happened to the moon, it happened to Earth. Essentially, as we have gone through the solar system with spacecraft since Apollo, Mars to the outer planet satellites to even places like Mercury and Venus, it has showed us that the history of the moon is the history of the solar system. So in large part, it's not too far to say that our entire understanding of the history of the solar system and the processes extant has completely changed as a result of the Apollo samples. The second critical part about Apollo that I think really matters is that we learned how to build robust spacecraft that could successfully complete a nominal mission and also could respond to contingencies in a way to bring their crews home safely. Apollo spacecraft had few single-point failures and dead ends that would affect negatively crew survival and mission accomplishment. Apollo 13 has often been described as a successful failure in that the scenario was something that had never really been practiced, and we had to make up as we went, but nevertheless successfully brought the crew home. The other accomplishments that I think are critical is the Apollo 12 landing within 13 meters of its designated point showed that you can land on planetary surfaces from orbit, and it's not just simply a matter of guessing where you land, that you could control a landing to a specific spot. In addition to that, the ability of the lunar module to accommodate an increase in lunar surface time and delivered mass to the surface was critical. The third reason why Apollo matters is that we learned how to do successful manned spaceflight. Prior to Apollo and the commitment to do Apollo, we really didn't know how to do what we do routinely now. The whole complement of forward control rooms, back rooms, mission support rooms, controllers, everything that we know now about how to do spaceflight grew out of Apollo. And without that, doing shuttle, doing space station would have been impossible. The fourth reason why Apollo matters is that we learned to build very large boosters, culminating in the Saturn V. The Saturn V could deliver to orbit the equivalent mass of the Atlas and Mercury spacecraft that we'd been flying to orbit only 6 years earlier. Without large boosters, shuttle would have never happened, we would have never built space station, and we certainly would have never done Apollo. The fifth reason why Apollo matters is that we learned how to do scientific exploration of a planetary surface with humans. This went from pressure garments that enabled the crew to get safely outside their spacecraft, portable life support systems that enable us to get well away from a landed spacecraft, rovers that could transport the crew to significant distances, up to almost 10 kilometers on Apollo 17 and potentially farther, and scientific instrument packages that could be installed on a surface and run reliably for years. So there is some sense in some scientific communities that I consider to be both ignorant and arrogant that little science was produced from Apollo. But as I alluded to earlier, nothing could be further from the truth. Everything we now know about the history of the solar system came from Apollo. And we got that information because we had crew members that could do the scientific investigation process. So there are a lot of lessons from Apollo for future exploration, but in my opinion, there's a number of really key ones. The first thing is that things break despite your best designs and plans. You should expect things that will break, train your crew members how to fix them, and fly your mission. The second is there's never enough time to do everything and see everything. So make a plan and stick to it. But don't get so hung up on the plan that when you find something new, like the orange soil on Apollo 17, you can't respond to it. The third thing is that the judgment of the crew on the surface is really better informed than the folks on the ground. And we should always listen to the people that are there when we're taking into account what's going on. The fourth thing is that navigation capability on the ground is a critical need. It's very easy not so much to get lost on the moon, but not really know how far you need to go and exactly the direction you need to go. And having navigational capability is critical. The fifth thing is that we need the proper tools and the proper procedures for the right situation. If you're taking a soil sample, you need to have the right tool to take a soil sample. Likewise, taking a rock sample. The sixth thing is you want to maximize crew flexibility. We send people to planets because their intellectual capabilities allow them to understand what's going on the fly. This is something robots can't do, and we need to always keep that in mind and maximize that flexibility. The seventh thing is when we have science station deploys, we should automate them as much as possible. Essentially, every Apollo crew who put the LSEP together grumble about how hard it was and that the fact that it took up a whole EVA. If we can automate that in the future, we should. However, anytime you automate something, go back to rule number one. Things break, and you should leave room for crew intervention, regardless of whether it's supposed to be automatically. The eighth thing is that you've got to keep your eyes open for unexpectedly useful things. A prime example is on Apollo 16, the crew executed right after landing something that was called the stand-up EVA, where Dave Scott opened the top hatch of the LEM and basically looked around from that high vantage point and developed his sense of what the landing site was like. That wasn't originally in the flight plan for 16. It was an idea Dave came up with, and it's the kind of thing we need to keep our eyes on. The last thing is that lunar dirt will be a pain, but it is not magical. It's not pixie dust. And there are solutions that can be found to mitigate its problems on the lunar surface when we go back, and we need to be constantly thinking of them. I'll finish this lecture by returning back to the quote from Charles Murray and Catherine Cox, that Kennedy's Apollo was a pile of chips pushed to the center of the table. The things that drove Apollo, the time spent, the innovation, the creativity, the pressure, all pushed back to that center goal that Kennedy put out there. And it led to us doing the best work I think this country has ever done. And we should keep that in mind when we go back to the moon.